Okay, hi and welcome to some video notes on solving nonlinear systems, and we're going to focus on doing that algebraically, which means that we're going to try to not use our graphing calculator. However, after this unit, and when you get a little bit further along, you're just going to want to have to graph these. It's going to be far easier. But going back and checking it algebraically and understanding how that works is very important. So let's talk about what that is. A nonlinear system sounds a little funny, I'm using that name, but there can be a linear function involved. Just wanted to make sure that we're super clear on that. What I mean by nonlinear system is that there is at least one function in there that it's not linear. And you can see that from my three examples here I've got drawn out, that there is a quadratic involved with all of them. So we're going to really be exploring a quadratic function and a linear function and their possibilities of solutions. Now remember, a solution then is the number of times that these functions intersect. That's always true for any system. A system is where they intersect and how many times that's possible. That's what you're looking for. So now knowing what we look for, we know that there's three possibilities because of this quadratic function is interaction with this linear function. We can have two solutions where the linear function crosses the quadratic function, and you'll see that these two intersection points are the things that we're after. So when we solve this, we're going to find these 2 points. And then coincidentally, we also have a single solution where it touches it just once, and there's the possibility of not having a solution at all. So those are the three things, which to us means that we must check for erroneous solutions, meaning that solutions that don't work, because when we check this, it may indicate 2 points, but they're not going to be solutions. So we're going to have to plug them back in, or we're going to graph them to visually see if those are valid solutions. So that is a must do here, is you must check your solutions once you've done. So let's go ahead and get right into this. Our goal, just like any other systems problems that we have, is to find a way to eliminate unknowns. We've got two equations. We need to get it down to essentially one equation and one unknown. If I'm looking at example number 1 here, I've got a quadratic unknown term, I've got a linear unknown term, and then I've got another one down here. There's a couple ways that we can attack this, but I'm going to go ahead and say, look, I've got f of x equal on both, and if that's true in standard form for both quadratic, right, and the linear, then I'm going to set them equal to each other and go ahead and combine them into one equation on one side. So that's going to look something like this. I'm going to take the quadratic x squared plus x minus 2, and I'm going to set equal to negative x plus 1. Why can I do that? I mean, really, if you want to get down to what we're doing, we're substituting. I'm saying that this linear function here is equivalent to f of x, and that's the f of x that I'm replacing it into. So I can set them equal. That's the short and sweet of it. So now that I have them equal, what do? Well, I'm going to use my order of operations, and I'm going to try to set them equal to 0, which means to solve. So of course that's what I'm going to do. So the first thing I'm going to do is I'm going to add x to both sides. And while I'm doing that, I might as well go ahead and move this 1 over as well. When I do that, look what happens on the right. Both of those two terms turn to 0. Great for me. That's exactly what I want to see. Now I'm ready to solve. Well, what am I solving? Well, I'm going to end up with an x squared plus x, it's 2x, and negative 2 and negative 1 are going to make negative 3. I'm going to solve that. Yeah, that's right. That's what happened. I took a linear equation and set it equal to a quadratic, set it all on one side, and I still have a quadratic function. Just a single one. Yeah, 2 went into 1. That's how it works. So with this single equation, or this single quadratic equation, I have some ability to solve this, right? I've got a couple methods that I'm going to use. I can use the quadratic formula, probably my last resort, or if my favorite, maybe I start with that. I'm going to check to see if it factors, and of course square roots is another possibility that I can do here. So I like to factor quite a bit. This looks like it might be factorable, so I'm going to go ahead and put up an x. And my x goes a times c and then sums to b in the bottom. So a times c is 1 times negative 3 or negative 3, and I have to sum to 2. Is that possible? If it is, this is factorable. I believe it is. If I take a positive 3 and a negative 1, they're going to multiply to negative 3 and combine or add to positive 2, which means that this is factorable. Even better, the a value is equal to 1, which means that this is quick and easy as an actual factoring. I don't have to involve grouping. I'm going to get x plus 3 and x minus 1. Now, don't get me wrong. I picked this example purposely so that I could do this quickly. Well, now I've got that set up and it's factored. Now I can gosh, quick darn in a hurry here, set these equal to 0, these linear factors here, and I can solve them. So I'm going to find out that my first solution's x-coordinate is -3 and my second solution's coordinate is +1. No, that is not a point, -3 and 1. What those are is two x-coordinates, and I need to find the appropriate y-coordinate. So I have to go and find this coordinate. Well, let me switch my color so I can point it out and you can see it. I got to find that coordinate. So I've got two x values. I got an x1 and an x2. What am I going to do with them? How do I find their coordinating y coordinates? Well, I'm going to plug them back into one of the two functions, right? It doesn't matter which one, which to me means I'm picking the easier one, which is linear. So I'm going to take the linear function, I'm going to evaluate it at -3, and I'm going to take the linear function, I'm going to evaluate it at, we'll put it here, f of 1. So I'm going to evaluate this function twice. So f of 3 is going to go in, so I'm going to have a negative, which is right here, right? And then I'm going to put -3 in parentheses plus 1. Which means +3 plus 1 or 4. So my point becomes -3 and 4. I'm going to do that again with 1. So I'm going to have a negative, put 1 in parentheses, plus a 1. And I'm going to find out that that's 0, or the point 1 and 0. So those are my two solution coordinates. Now, in this way, we're going to check them. We're going to do it by algebraic method. In the next example, we're going to use a graph. So to check these algebraically, how do we know if those are solutions? Well, you plug them back in, both the x and the y coordinate, and you find out if they are true statements. So I'm going to plug x in here. Oops, that should be a y there. I'm going to plug those in back into both of these to verify that they're solutions. So I have to do this a couple of times. So I'm going to first plug it into the quadratic. So the quadratic function, I should not use y here really, right? I should be using f of x. So there's my f of x term. So I'm going to plug in 4. This is going back into my quadratic right now. 4, that's f of x right here. So I'm going to say 4 is equal to my x value squared, so -3 squared. And then I'm going to put plus -3. And then I'm going to put -2. If this makes a true statement, then it's a solution. So I'm going to leave 4 over there for right now. I don't need to move it. I don't need it equal to 0. I'm not solving. -3 squared is 9, plus a -3 minus a 2. So this makes -5, and -5 and a +9, guess what? It makes 4. So this is a true statement. So this solution checks for the quadratic so far. Excellent. Let's check the next solution, see if it makes a true statement. If it fails either equation, by the way, then it fails altogether. It has to be true for both. Really, you know what? Let's check this same point versus the linear next. So I'm going to go back to this -3, 4. Now I'm going to plug it into the linear and verify, and then I know that it's a solution for both. So I'm going to have 4 equals, right, because I'm plugging in for f of x, that's my y value, f of x value, equal to negative 3, right, plus 1. These two negatives are going to make a positive, and of course 4 does equal 4. So that checks. So this is a solution by our work so far. Now we're going to check it for the other possible intersection point. Because remember, we could have one solution like this that's kind of represented, or they could both be solutions when this one isn't the case anymore because we verified that one is a solution. So we're going to plug in x and f of x here. So my f of x, we'll start with the quadratic, is going to be 0. So 0 is equal to x squared, or 1, right? We're replacing it with the value of the x coordinate. So 1 squared plus 1 minus 2. So that's 1 plus 1 minus 2, and we can see already that that's going to turn into 0. So 0 does equal 0, so it checks for the quadratic. Now we need to check it for the linear. So I'm going to go ahead and plug in 0 for my f of x value equal to -1 plus 1, and then you can see that that's already going to turn to 0. So 0 does equal 0. So these are both solutions for this system, which means that we do have, of course, this first scenario there.